All right, let's get right into it. Today, we're putting two absolute titans of the welding world head-to-head, TIG versus MIG. Or, if you want to get formal, that's GTAW versus GMAW. And the battleground? Well, it's one of the toughest, trickiest metals you can weld, aluminum. We're going to go way beyond just technique and look at the metallurgy, what's really happening inside that weld puddle.
So why all the fuss about aluminum anyway? I mean, what makes it such a notorious headache for welders everywhere? Well, it all comes down to a tough, completely invisible barrier that's protecting the metal, but making our job a whole lot harder.
And here it is. Meet the villain of our story, aluminum oxide. This stuff forms instantly the second aluminum hits the air. But check out those melting points. The aluminum underneath turns to liquid at around 1200 degrees Fahrenheit, but this oxide layer on top won't even break a sweat until it's over 3700 degrees. It's like trying to melt a chocolate bar that's trapped inside a ceramic mug. If you don't get rid of that mug, you're just not going to get a good weld.
Okay, so here's how this showdown is going to go down. First, we'll break down the challenge itself and properly introduce our two contenders. Then, it's a three-round fight. Round 1 is all about cleaning the surface. Round 2, controlling the heat. And round 3, we'll look at the final microstructure. After all that, we'll head to the judge's decision to see which process wins for which job.
You know, when it comes right down to it, the biggest, most important hurdle in welding aluminum is beating that oxide layer. It's the gatekeeper. It's what decides if you end up with a strong, perfect weld or a weak, contaminated disaster.
See, this oxide layer doesn't just get in the way. It actively tries to ruin your weld. If you just melt the aluminum underneath it, little flakes of that tough oxide can fall right into your molten puddle. These trapped bits, or inclusions, are basically like having tiny pieces of sand in your weld. They create weak spots that can cause the whole thing to crack and fail later on. You have to get rid of it as you're welding.
All right, let's bring out our contenders. In this corner, we have gas tungsten arc welding, better known as TIG. And in the other corner, gas metal arc welding, which everyone just calls MIG. They both use an arc and a shielding gas, but how they get the job done, well, that couldn't be more different.
Okay, so the biggest difference really boils down to this. With TIG, you've got a tungsten electrode that doesn't melt, and you use your other hand to carefully feed in a filler rod. It's a two-handed operation, which gives you incredible pinpoint control. Now with MIG, the wire you're feeding is both the electrode and the filler metal all in one. It shoots out of the gun continuously. It's way faster, but that speed comes with some trade-offs.
All right, ding ding, round 1. This is maybe the most important round of all, the cleaning action. How do these two processes manage to punch through that stubborn aluminum oxide so the metal can actually fuse together?
Well, the secret weapon for both of them is electricity. More specifically, it's about which way the current is flowing, the polarity. When you're welding aluminum, the magic happens when the electrode is positive and the workpiece, the aluminum, is negative. We call this electrode positive.
So here's what's happening on a microscopic level. It's pretty cool. When that electrode is positive, a stream of charged particles, or ions, literally bombards the surface of the aluminum. It's this thing called ion impingement, and it acts like a tiny, high-powered sandblaster. It just cracks and vaporizes that oxide layer right in front of your weld puddle, clearing a path for the clean metal to join together.
Okay, so the surface is clean. We move on to round 2, heat control. And heat, well, it's a real double-edged sword. You absolutely need it to melt the metal, but too much heat or heat in the wrong spot, and you're going to get warping, distortion, and a weakened joint. It's a delicate balancing act.
Now, compared to something super high-tech like laser welding, you can see that both TIG and MIG are actually pretty forgiving. You don't have to be perfect with your torch position or the gap between the pieces. But here's the real kicker. The total amount of heat they pump into the metal is vastly different, and that has huge consequences for the final weld.
TIG is the undisputed master of low and slow. It uses lower heat input, which gives the welder amazing control, and that makes it perfect for really thin materials. The trade-off? It's slow. MIG, on the other hand, is the speed demon. It's a high-heat, high-speed process that just dumps energy in to weld fast, which is great for thick plates. But all that extra heat creates a much larger heat-affected zone. That's the area around the weld that gets cooked and can lose some of its strength.
But what if you want the speed of MIG without all that blistering heat? Well, that's where some really clever innovations come in, like cold metal transfer, or CMT. It's basically a modified MIG process where the machine physically pulls the wire backwards for a split second with every single drop of metal. This simple action dramatically lowers the heat input. It's a total game changer, letting you use a MIG-style process on super thin aluminum or even to join aluminum to steel.
All right, on to our final round, and this is where we get a little nerdy. The final microstructure. After the welding is done, the arc is off, and the metal has cooled down, what does the grain structure inside actually look like? Because this, right here, is what ultimately determines how strong and tough that weld is going to be.
So why should you care about grains? Well, in metallurgy, a good rule of thumb is that smaller is almost always better. A fine, uniform grain structure gives you better strength, better toughness, and makes the weld much more resistant to cracking. Because TIG has a bigger weld puddle that cools down a bit slower, it tends to create a really nice, fine, equiaxed grain structure, which just means the grains are all roughly the same size. The high speed and faster cooling of MIG creates a different kind of structure that you have to manage really carefully.
And this is exactly the risk you're trying to manage. Now, don't worry about every detail on these charts. They're showing results from tests for solidification cracking. The main takeaway here is that for both processes, this is a real danger. It all comes down to choosing the right filler metal for your base metal to control the chemistry and prevent those tiny cracks from forming as the weld cools.
So, after 3 intense rounds, who's our champion? Who's the winner? The truth is, there isn't one. There's no single best process. The best process is the one that's right for the specific job you're doing.
So let's look at the final scorecard. When it comes to cleaning action, TIG wins on points for its precise control. For heat input, TIG is low and controlled. MIG is high and fast. That directly affects the microstructure, where TIG often gives you that finer grain structure. So here's the bottom line. If you need absolute precision, total control, and a beautiful weld on thin material, TIG is your champion. But if you need pure speed and efficiency on thick material for long production runs, MIG takes the belt, no question. And that's really what it all boils down to. It's the classic trade-off, right? It's the careful, meticulous art of TIG versus the raw, high production power of MIG. One isn't better than the other. They're just different tools, designed to produce different results for different applications.
So, understanding what's going on inside the metal is really the first major step. The next, of course, is getting out there and practicing. So now that you know the trade-offs between precision and speed, which one of these amazing tools are you going to master first?